And in the last unit of study, we're going to be looking at electricity. So first, we're going to be looking at the power plant. And the power plant, we have the electrical wires. They go to the various, what is this called? Amplifiers, I think it's called. Then transformer, and eventually to your house. So the first question that we want to try to answer here is, what is electrical energy? And this is where you can help me out. No one knows what electrical energy is?
Electricity.
And what is electricity?
Energy.
But energy due to what?
Electrons?
Friction.
Yeah, close. So remember, so far we only studied energy due to position. So in other words, the configuration of an object. So if you have an object that's at a certain height, it has potential energy. And then we looked at another type of energy where an object is in motion, which is kinetic energy. So electrical energy is the energy due to motion of the motion of what?
I think Char got it.
Electrons.
Now Chow is really smart, but in the test she kind of messed up a little bit. She's right in this case though. But in electricity, she's actually wrong because we follow conventions and we don't say that the electrons are moving. When we talk about electricity, we talk about the motion of protons. Now, this is not the car Malaysia. This is actually the elementary particles. So you could say is the energy due to motion of electrons, which is actually correct, but we are going to say that it's actually the energy due to motion of protons. Now, one way to get around this is to just call these two charges. So you can just say it is the energy due to motion of charges if you want to be correct, because it depends on who you talk to, right? Some people will be like, oh, electrons is correct. Some will say protons are correct. They're both correct, which is the confusing part of this unit. And you know who made this to be very confusing? It was the Americans.
Oh, so you hate Americans.
Yeah, so there was a famous scientist, you know, Benjamin Franklin?
And Ben Shapiro.
Ben Shapiro? No. So Benjamin Franklin, he's kind of like the father of electricity. And in all of his findings, he always assumed that the protons were moving. But it turned out that the electrons are actually the ones that are moving. But because we want to pay respect to the American, we say protons are moving to make them happy.
That's so stupid. So are we just going to be using electrons just for like the sake of like integrity?
So this is where the split comes into play. So what really happens and the other one is what we say happens. Kind of like what's going on today, right?
Yeah, Biden wins and then they say that Trump won.
Okay, so the Americans are so entertaining. They're always doing all sorts of things to keep us talking. So it turns out that this motion of charges is what we're going to be defining as our electrical energy, and another way of saying it is just electricity. So if we look at our wire, we can represent the protons, and the protons are the ones that are moving, and they're moving to the right. But you know, this wire, I drew it very thin, so if we were to zoom in, you know, today I was using Zoom. It was so difficult because I'm covering one of Ms. Melendi's classes. It's so complicated. So if we were to zoom in, we suspect that the wire has some kind of thickness, right? And what we're going to do, we're going to cut a cross-sectional area. So this means a small piece along the wire. So cut across. And imagine trying to stand by the side in this cross-sectional area, and what you're going to do, you're going to see how many protons are moving in a given time interval. So again, it's kind of like trying to be a detector, like, all right, in this cross-sectional area, I want to see how many protons are going through in a given time interval. So it turns out that this is going to be our definition of the word current.
Wow.
So this you're familiar with, right? You used this word before, but you didn't know the technical, the technical definition. So in this definition of current, again, we have two types of currents. We have the conventional current, which is the protons that are moving, and we have the electron flow, which is the electrons moving. So normally when people always say the word current, what they really mean in full is conventional current. Now, just from this definition, you could come up with a formula for this, right? So the number of charges moving past a cross-sectional area in a given time interval. So current is going to be the ratio of the number of charges over a time interval. And here we have a new symbol. Q represents charges, and delta T we already know, right? Time interval.
Can we say electrons instead of protons because that's technically what's correct?
No, but then in electricity, everyone takes it to be this convention. So even when you do like the analysis, we have to assume the protons are moving. So again, it's one of those annoying things about this particular unit that we have to learn something that's not really happening, but it turns out that it does a better job at explaining what is happening. All right, so now we have this idea of current is the number of charges moving in a given cross-sectional area during a time interval. And charges is just either the number of protons or the number of electrons. But we're going to say conventional current, so we're looking at the number of protons. By the way, does anyone know what the unit of charge is? No, right?
Mole. Excuse me?
What is the unit of measurement for charge?
I think Max got it right.
The mole?
Yeah, the moles.
No, the mole is the number of particles. Actually, a large collection of particles.
Electric charge?
Whoa, Coulomb. Yeah, that's right.
Oh, Coulomb. Coulomb.
Cancun.
Yeah, is the Coulomb. You know, this word I actually have such a hard time pronouncing. Coulomb, Coulomb, Coulomb. But in Spanish, this word means but. So that's why I find it so hard to pronounce. Yeah, so we measure charges because Coulomb means but. So Coulomb,
Which but?
but. Like Glorious Maximus, they call it, the scientists.
Well, what's a different word for that? How do you spell it?
Is this doesn't matter. All right. So the Coulomb, we use the letter C. And time interval, that's seconds, so S. So this new current, we're going to be measuring it in coulombs per second. Now this is a derived unit, so it's not like a foundational unit. It's a unit that we get by combining other units. So the coulomb per second is the ampere. You're supposed to... yeah, try to pronounce it with a French accent. So you guys took French, right?
Armpit.
No, not armpit, ampere. Like, I don't know.
Ampere.
But, you know, Americans are now going to try to pretend a French accent, so they say amps. So we say amps instead of amperes. So coulombs per second is just the amp. It gets the capital letter A.
So Miles,
Yeah, Ian?
what is ampere?
I? Current, conventional current.
Okay.
What's the difference between that amperage
And what?
and amps?
No, amps is just the unit that we use to measure the current. So we could say we have 6 amps going here.
So it's the same thing as conventional current?
So 6 amps will be 6 coulombs per second. So amps is just the unit of measurement. So 6 amps is 6 coulombs going through the cross-sectional area in 1 second of time. If you say 12 amps, then you have 12 coulombs per second. Sense making?
Yes.
Wow, your teacher must be so good. You can explain it so well. So maybe when you do that teacher evaluation survey, you're going to write nice things.
Are you gonna stop being nice after that's done?
No, I only have one mode in my personality. It's just nice all the time.
So you're a nice guy?
Actually, I'm not. That's a lie. All right, so now we've seen electricity is the movement of charges, and we're going to restrict to positive charges moving, which is conventional current. But if we have charges that are moving, we need to think back to the previous unit of study. How do we make charges move? How do we make things move?
We cause an imbalance in polarity, right?
No, you're trying to think too far ahead. Instead, think back
Energy.
to what we talked about in Unit 2. So how do we make a block move, the most exciting object in physics?
Is force.
Yeah, so whenever you want to make anything move, you need an unbalanced force acting on it. So if we think back to our tomato, or apple, whatever you like. What makes this apple fall? That there's a force of gravity acting on it. So in other words, to make charges move, charges are objects as well, they need to experience a force. But before they experience the force, what needs to be present in the area? So remember back to Unit 2, the force is only activated when an object interacts with the... That's a fill in the blank. With the...
Acceleration.
With the acceleration. Let me help you out. So the formula for the force of gravity is mg. So you have a mass, it interacts with g. Now this G, we called it the gravitational field. So we were saying before that there's a field present in space due to the mass, and whenever another mass comes in the field, it activates the force. Then this force makes the object move. So we were to think about charges. What are we going to have? There has to be a force to make it move. We're going to call this the electric force. But just like before, instead of mass, we're going to talk about the charge. And instead of the gravitational field, we have the electric field. Do you see the similarity in the formula? By the way, we won't be using this formula, so don't worry. This formula we won't be using because
So
we're
why
not.
are you teaching it though?
Well, normally I do teach it because there'll be lesson 3, but we're not doing lesson 3.
Are we having a test for this unit too? Please no.
Yeah, 100% for sure.
And what's the weighting now?
Weight 5. So it's pretty much your CCT, you could think of it.
The exam's 30%, right?
Yeah, that one's at 30%.
Oh, Chia, you messed up a test with weight of 4.
Yeah, Chow, why did you write not enough information for both? Both of them had enough information.
I don't know.
You panicked.
Yeah, I bet. Had like 5 minutes left, so I was like, okay.
Oh.
More or less.
Josephine, you were so
Very
quiet today. You fell asleep?
No. Can we not have final test?
No. Yes, I back that.
How
Can
many
we not
questions
have
would that
final
be?
test?
Well, we can talk about it next time. Like,
Oh, it's negotiable. Okay.
Or just leave the test, right?
yeah, the art of the deal.
Do you last minute make the test one?
You quit. Don't ask difficult questions.
So this is how I make the test. So I go on Google and I type physics questions for grade 11 and I just put it in the Google form.
All right. So back to this. So how do we make charges move? Well, the same way that we make anything move, we need a force acting on it, and for that force to be present, there needs to be a field. So here we have a field, the charge interacts with it, then it makes it move. So that's one way to think about motion, right? But then what if we were to think about energy changes instead? How can we explain the apple falling due to energy changes?
Potential energy becomes kinetic or gravitational.
Wait, say louder.
Potential energy becomes either gravitational or kinetic energy.
Wait, potential becomes gravitational?
No, potential becomes kinetic.
Okay, yeah, that makes more sense. So we have an energy transformation occurring, right? So the potential energy is due to the object being raised from some height. So potential energy is the energy due to the configuration of the system, which is a fancy way of saying due to position. So because the tomato is some height above the ground, it has some potential energy. And what happens with that potential energy? It gets converted into into kinetic.
Good.
So this is the best part about electricity, because we took so much time to understand the difficult idea for apples and tomatoes. Now we can apply for charges. So what's going to make this charge move is in some given position. Due to that position, it's going to have potential energy. And what is it going to do with that potential energy?
Convert into kinetic.
Into kinetic. Now the only difference is that for gravity we say gravitational potential energy, and what are we going to call it for charges?
Electrical?
Yeah, or electric potential energy. Kinetic energy remains kinetic energy. That one stays.
Okay, for gravitational potential energy, it's based on how high you are. With electric potential energy, it's based on what?
Perfect. That's exactly where I was going next. So gravitational potential energy depends on the change in height. So remember the formula for the change in gravitational potential energy was mg delta h. So it only depends on the change in height. Now for electric potential energy, we don't have a mass, so instead of the mass, what are we talking about? A charge. So you see the previous comparison that I was doing? Instead of mass in the formula, we use charge. Instead of gravitational field, we use electric field. But now for electric potential energy, it depends on the change in what we're going to call the change in voltage. Oh, you can't really see the yellow, right? Oscar?
Referring to Oscar, right?
Yeah, 'cause, Oscar can't see colors like we can.
No, I can see that fine.
Oscar sees in black and white.
You know, dogs see black and white too.
Oh, no, wait. No, actually, dogs don't see.
No.
They don't. Because humans have 3 color codes, dogs have 2, so they see less color than us, but they still see color.
Really? So you can see me?
Is the explanation because they don't know how to cross? That's why.
Yeah, like there's like this shrimp in the water with 16 color codes. Humans only have 3.
Life was much easier when we used to be fish, right?
What?
Yeah.
Yeah, we used to be fish. All right.
I thought you denied human evolution.
No, you can hold two simultaneous truths at the same time. This is the new. This is our new generation. We can hold multiple truths at the same
So
time.
what was Genesis?
Yeah, what was Genesis? Alex? Namaste. Is that your answer?
No, that's a good question. You know, I started to read the Bible again. Actually, I'm trying to analyze it more. All right, but let's talk about electric potential difference. Now, this is where it gets complicated. So the change in voltage, you have some familiarity with it because you were working with circuits before, so you know what the voltage is. Well, you never knew what it was, actually. You measured it. But in physics, we call this the electric potential difference. So for our apple or tomato, it depends on the change in height. For this charge, it depends on the potential difference. This potential difference is what we call the voltage. Now, it won't make sense 100% today, but we're going to be talking about voltage in a lot more detail tomorrow and on Friday, because that one's actually a very complicated idea. But do you get the basic of it?
Yes.
It's basically just difference in electric energy, right? Hello?
Yeah, I'm thinking your answer. Well, one analogy that people use is they have like a height to represent like a waterfall. So when you're up on the top of the waterfall, you have some potential energy. And as you're falling, it turns into kinetic. So it's the same thing with the electric potential. So when you go from a high potential to a low potential, you're going to be speeding up or slowing down.
Speeding up.
Yeah, so it's likewise, like when you're falling, you speed up. But now imagine trying to be a charge and go in the other direction. You will be slowing down. So the same idea, same idea. So now that we know what is moving in electricity is charges, which is protons. We know how to measure the current, and they move because there's a potential difference. And the potential difference is what's going to make these charges move along the wire. So that's where they say there's a potential difference, like high voltage zones, right? You might have seen the signs. So the voltage is just making the charges move. If there's a voltage difference, it has to be a difference. If the voltage remains the same everywhere, the charges don't move, because it's kind of like the height staying the same. The tomato won't be able to move, right? It's just going to stay on the ground. So you need to have a height difference or a potential difference.
So you need a voltage difference for the thing to move.
Yeah.
So I can imagine like a higher voltage and a lower voltage, and the electric charge is trying to, like fall over, down, pour into it.
Yeah, yeah. So that's why usually you can think of the power plants as having high voltage. And when it gets to your home, you hope it has low voltage. And then you have a potential difference.
I'm not supposed to understand this equation yet, right? Because we don't know voltage.
Yes.
Oh, this equation? No, not yet, not yet. We're going to talk. Voltage is one of the most highly searched topics on YouTube because it's hard to explain, really hard to explain, and hard to understand.
Where do you get that info?
Physics.
Wait, say it again.
The most highly searched topic regarding physics.
No, for the electricity,
Yes.
Alright. So not even physics.
that?
Okay.
No, nobody likes electricity because it doesn't make sense. And the reason why it doesn't make sense is because of this electric potential, the voltage.
Then why are we learning it?
Because what if you guys want to change the world and be like climate activists, and then you're trying to create sustainable energy methods, so you need to learn about the electrical grid.
Summarize, would you go back to a hunter-gatherer lifestyle if you had the choice?
No, I would have died by I wouldn't have made it this old. Okay, so now let's have one more slide. So we have the power plant. Transformer, and into your home. Now, once it goes into your home, so we know how it gets there. But once it gets into your home, let's say you want to light up your TV. Your TV usually has a power rating. Have you seen those on the stickers?
Yeah.
So power rating is usually given in, well, what are the units for power?
Volts.
No, think back to the human power lab.
Watts.
Joules.
Yeah, because power, what's the formula for power?
Max left.
Max left. Power is going to be the work over the change in time. And how do we measure work? In joules, and the change in time in seconds. Joules per second is the units of what? So when you see a power rating, they'll give it to you in watts. So if someone says the power rating of a TV is 1,200 watts, how much energy does it need for 1 hour of usage? So power rating is how quickly energy gets converted in a given time interval. Remember, the definition of power is work over time. Work is the transfer of energy. So another way to think about power is how quickly energy needs to be transformed. So if we have a power rating of 1,200 watts, this means that you need 1,200 joules per second. So how much energy do you need for 1 hour? Anyone?
Mr. Morales,
Yes, Josephine?
do we have to convert hours into seconds?
Yeah, that's why I wrote joules per second, so that way you can see you need to have seconds.
Mr. Morales, I have a question.
Yeah?
If like a more powerful, that's like, okay, if a power plant transfers the power to a less powery power plant, would there be more or less energy compared to when a power plant is transferred to like a home? Since the difference between the two power plants is lesser than the one at home. The voltage.
Now, this is my fault because I made it look like the current is always moving along. But there's two types of currents we're going to look. So I'm going to answer your question later on. There's DC and AC. So I can't answer your question yet because we need to look at the difference between DC and AC. So when I put the direction of current, I'm not 100% correct because this power system, I mean the power grid, is actually AC. So there's going to be a really funny video we're going to watch later on with Tesla versus, not Tesla, what's his name? Yeah, Nikola Tesla, yeah, that's his name. Tesla versus the other guy, what was his name?
Edison?
Yeah, Edison. I can't believe I forgot.
Oh, you're a teacher.
I don't know, I guess in Canada it's
Wait a
easy.
minute.
Well,
No.
since you're conservative, that means you applied for your degree, right? How much did you pay the guy?
No. All right. So, Max, for your question, we have to come back to it after we talk more about DC and AC, all right?
Noted.
All right, so for this particular question, they're asking you how much energy is required. So if you look at the formula for power, is work over the change in time. But work is actually the transfer of energy. So another way to think about it is the change in energy over the change in time. So if we want to isolate for how much energy is needed, we just need to multiply power by the change in time to give us the change in energy. So the power rating was 1200, and we multiply that by 1 hour. And what do we get? 1200 watt hour. So this is the same thing as 1.2 kilowatt hour. Hey, Oscar, stop. I'm trying to show something. So one way that we measure energy, we can measure energy in terms of joules, or what's commonly used for electricity is the kilowatt hour. So now you see where that comes from, right? Because the formula for the change in energy is the power times the change in time. Power has the units of watts. Time, you can use hours, so that's where you get watt hour. Then there's 1,000 in a kilo, so you can convert this into kilowatt hour. But if you wanted to use joules, then you just have to convert the hour into seconds. Who did this? So here we have 1200 watts in 1 hour. How do we convert that to seconds? So we wouldn't be doing division, we have to multiply by 3600. Do you see the difference?
Wait, what's the difference between the kilowatt hours and the second one when you multiply?
Yeah, because the second one, we changed it to seconds. So what's going to be watt times second? A watt is joule per second. So what's joule per second times second? It'll just give you joules.
Oh,
So when you're talking about electrical energy, if you look at your bill, like your Tenaga Nacional, it's going to be in kilowatt hour. But if you want to do it in physics, you're going to use joules. So you have to get this really, really large number. Did anyone calculate it?
I would if I fully understood what's happening.
Which part you got confused?
I don't know, the law of letters, man.
Yeah, so that's going to be a really, really large number. So it's not very convenient to work with joules because you're going to get really large values. But you see kilowatt hour is 1.2. Okay, let's go to the next slide. Okay, so we these are the main formulas that we have to keep track of. So So now we know how to measure current. Current is the charge over the change in time. And notice that for charge, we could either use a capital letter Q or the lowercase letter q. So that's why I put the or. It's the same thing. And we saw how to measure the electric potential energy, which is going to be the charge times the electric potential difference, which is the voltage. And power, we already saw how to calculate power from before. It's just the work over the change in time. But since we're talking about electrical energy, work is how quickly the electrical energy is transferred. So it's going to be power is the change of electrical energy over the change in time. So we have 3 new formulas now. Well, not really new because we already had the power formula. Did you follow that? So for current, the SI units of current is the, what is the SI unit of current? The ampere, which you said amps, or we could use the letter A. What about for charge? For charge, we say the coulomb, which we use the letter C. And now the one that I didn't mention before is of delta V. Which is the electric potential difference. But that's in the name itself, right? So electric potential difference, we call it the change in voltage. So the units that we're going to use is the volts. So the capital letter V. So it is a lot of units introduced. And that's because technically from the textbook, I covered 11.1, 11.3, and 11.5. So we did 3 sections in this one lesson. You guys are amazing. You could handle so much. The students are great. The teacher's great. When you have time to do your teacher evaluation, you're going to write great things.
Oh, right now we can do the teacher evaluation.
What does E represent again? Change in E. What's E again?
Change in electrical energy. Or just energy.
And P is watts, right?
Yeah. The part that gets annoying is because the formula for power is W over delta T, but this is W from work. So that part does get confusing. I'll give you that. Now the rest of the slides, it just has a couple of questions for you to practice. So try to practice a few questions.
What is I conventional current?
Because we said what's really flowing are the electrons, but because most of the papers, most of the written work was done with protons moving, we do it out of respect for our forefathers. Kind of like people trying to respect the Constitution, right?
Okay, then what is the variable I?
No, it's just the letter. I is current. Yeah, why did they use the letter I? That one I don't know. Maybe it's a Latin word.
That's what I'm asking.
Well, where I'm leading us into is going to be looking at circuits.